So we are discussing with the efficiency of a single phase transformer, and just telling that efficiency is to be calculated on the basis of kilowatt. So what you do, you take the ratio of the output kilowatt and the input kilowatt. Now, in case of a transformer, if S is the kVA rating, if S is the rated kVA, and cosine theta is the load power factor, then the output power in kilowatt will be X into S into cosine theta. And also you recollect that P core is the core loss with rated voltage applied, This core loss remains constant from no load to the full load condition. It does not change. So it is basically constant. Once the transformer is loaded, it does not change. And remember also that PCU is the full load copper loss. And X is the per unit loading or fraction of loading. X is the per unit loading of the transformer. Or sometimes you can call it also degree of loading of the transformer. It will be generally a fraction lying between 0 to 1. The value of X equal to 0 indicates that the loading is 0, output power delivered is 0, and when X equal to 1, the kVA handled by the transformer will be SKVA, like that. And cosine theta is the power factor of the load. Now, under this condition, we note that P copper, that is the copper loss of the transformer, as you vary X, will go on changing, and P core is constant. Now, let us assume, let the load power factor cosine theta be constant. Okay, cosine theta we are keeping constant, but we are varying the magnitude of the load impedance, keeping the ratio of RL and XL constant. That way we are varying. That is what I am doing is, that is, this is the transformer. Here this is the load impedance, which I am varying. Z2 load impedance. Suppose RL plus JXL. This load impedance I am varying, but in such a way that both RL and XL I am varying. In such a way that XL by RL, this ratio remains constant, such that I will be able to draw different amount of current from the transformer, imposing different loading on the transformer, keeping the power factor constant. This will ensure cos theta constant. This way I will vary. Now, under this condition, we would like to find out, does there exist any condition for maximum efficiency or not in the transformer. So, we want to find out the condition for maximum efficiency, That is, once again, this eta, we write it as XS cosine theta over XS cosine theta plus of XS square P copper plus P core. To find out the condition for maximum efficiency means that we want to find out at what degree of loading the transformer should be operated such that maximum efficiency will occur. That is, at what x, the transformer should be operated for eta max. Obviously, you have to differentiate this expression then with respect to x, because other things are constant. S is the kVA rating of the transformer. Cosine theta, I have kept it constant by varying Z2. P copper, this factor, is the copper loss under full load condition. So that is also constant. And P core is the core loss that remains practically constant from no load to full load. However, before you start differentiating it, you just arrange it in this way. You divide the numerator and denominator by x so that the steps will become easier. So this will become, you divide by x, both numerator and denominator. So then this will be x TCU plus P core by x. Obviously, for eta to be maximum, the denominator should be minimum. So you simply differentiate this one, that is ddx of s cosine theta plus of x PCU plus P core by x, set it to 0. So just for easier steps, we have divided the numerator and denominator by x, and you differentiate it. Now if you differentiate, then obviously you will be getting it like this, that is PCU minus of P core by x square equal to 0. Or you will get that P core is equal to x square PCU, and the value of x at which maximum efficiency will occur will be given by P core by P copper. So this is one very useful relationship, because if a transformer is given, then you would like to know at what loading the transformer will give maximum efficiency. And given a transformer, this can be easily also calculated. How? What you have to do to calculate the value of x? You have to do simple short circuit test. Short circuit test will give you the value of P copper. At rated current you take that. P core will give you the no load test wattmeter reading. Take the ratio, take under root, and this value will lie between 0 to 1 generally. Suppose after calculation you find this value becomes a 0.7, and just to give you some idea, suppose you have a transformer whose rating is 100 kVA. Suppose a transformer rating is 100 kVA. After knowing the value of P core and P copper, you calculate x. Suppose you get the value of x to be 0.8. That means maximum efficiency will be obtained when the transformer will be loaded to deliver 80 kVA. It means that. Okay. Anyway, at this point I will highlight further. But now, if you plot this one, that is on this side the degree of loading x, and on this axis efficiency, eta, then this curve will look like at zero loading the efficiency is 0, because output is 0. It will pass through origin. But anyway, this curve suggests that it will be somewhat like this. And there will be this eta max. and this eta max will occur, this value of x is this one, P core by P copper. This is the value of eta max. Of course, we should attach to this curve one parameter. What is that? This curve we have obtained at constant power factor. So I must attach a string to it, that is at a given power factor. Is not cos theta I have assumed constant. So at a given power factor, cos theta say 1, or cos theta, let me write cos theta constant. Now the question is, therefore for a given power factor we have seen that, for a given load power factor we have seen that eta max I know how to calculate and get it. But suppose now let us open the things in this way. Power factor also will vary, and I want to find out what will be the efficiency of the transformer. I mean, what will be the condition for maximum efficiency of the transformer at that load. So to tackle that problem, what I will do it now in this way. This you just follow. The derivation is very simple. Now suppose for a given power factor, this is the efficiency versus degree of loading curve. Now what you do, you draw a vertical line here at any point you like, and keep the loading fixed and go on varying the power factor. That is what I mean to say, that now I mean the title should be to understand how eta changes with power factor. That constant I will remove now with power factor. What we do is this: you fix up the loading, that at that loading I will operate the transformer. Fix loading. That is x into s I will keep now constant. At any point I like. Suppose at this value, whatever is the kVA, that x I will not remove. And I will go on changing the power factor of the load. This also I can realize. Are you getting? That is, the load impedance Z2 I will vary in such a way. Power factor changes, and also the magnitude of impedance changes. I mean, magnitude of impedance remains constant, so that kVA will be constant. So if you do like this, then in this expression, fixed loading, that is efficiency, is equal to, will become now S1. Suppose this I call it S1, some fixed loading S1 into cosine theta divided by S1 cosine theta plus this copper loss, whatever is the value of x into P copper. P copper is the fixed loading, plus the core loss. These things are there. But what I am trying to tell, the moment you fix S1, the kVA loading, which is equal to x into S, that is there, then this copper loss and core loss, both of them will become fixed. Core loss is fixed, no doubt. You imagine that the transformer loading is varied in such a way that the kVA at which it is operating is constant, so that copper loss will remain constant. You are only changing the power factor of the load. So that can be understood if you draw a, that is what I am trying to do. I am fixing the kVA now at which the transformer will operate. That is fixing the value of x at some arbitrary point, but once I fix that, I will not move from that point. Then I am changing power factor, cosine theta I am changing, keeping the loading of the transformer constant. Now, if you keep the loading on the transformer constant, what will happen to the copper loss? Copper loss at a particular degree of loading remains constant, no matter how you change power factor. That is x into s you are keeping constant, which I am calling cos theta. X into S1, which I am calling S1 here. So output power will be S1 cosine theta. Here what I am changing is only the cosine theta. This is the variable part. This is the variable part. So tell me, under this condition, for a given loading, at what power factor efficiency will become maximum? 1 it will be. Because if you bring cosine theta down, this cancels out and you can easily differentiate and get this one. So eta will be maximum for a given loading, for a given loading, eta will be maximum at cosine theta equal to 1. That you can easily verify by differentiating it with respect to theta. That is, if you do that I will not do d theta set to 0, find out theta. This will come to this. Then how the efficiency curve will now look like? I will respond to you slightly later. So efficiency versus x curve will now look like this. This is the efficiency versus degree of loading for say 0.8 power factor. What do you think the efficiency versus x curve will be for power factor 0.9? Above. And it will be like this, same shape like this. Where will be, this is suppose 0.9 power factor. For unity power factor, this will be the topmost curve. That is, for a given loading, lowest efficiency will be at the lowest power factor. That's all. So you are drawing a family of curves. This is suppose unity power factor. Okay. Anything?
Sir, from the expression of x, we see that it's given by square root of P4 by P copper. Right. So, is it necessary for all transformers to have P4 less than P copper?
At that point, I am just coming. So this will be the thing, efficiency versus x curve for different power factors. Another point I would like to tell at this point, it does not depend upon, the efficiency does not depend upon whether it is a lagging 0.8 power factor load or leading 0.8 power factor load. For to this curve, do you think should I attach to this power factor parameter for a given curve anything like leading, lagging? This is not necessary, because this cosine theta takes care of that. It is positive in both the cases. So both for leading 0.8 power factor or lagging 0.8 power factor, it will be same like that. Now the question is, therefore, from the use point of view, knowing that the efficiency versus degree of loading curve for a given power factor will be this way, we can at least say this much: the maximum efficiency will be obtained. We should see that the power factor of the load is unit. These are all the points corresponding to maximum efficiency, where x equal to this root over P core by P copper is not. Maximum efficiency point is this one. Now, if it is 0.8 power factor efficiency maximum, you can have this one. So highest one can obtain at unity power factor. Therefore, if I want to operate the transformer at unity power factor, perhaps we will say that let the transformer be operated at unity power factor such that the maximum possible efficiency one can derive from the transformer. However, as I told you, that the nature of the load really is not in your hand. There will be induction machines, fluorescent lamps, which make a power system always lagging power factor, that you cannot make it strictly unity. There are so many loads, different kinds of there. And zero 0.8 power factor is somewhat maintained. Users are told like that, industries try to maintain, and for that they use power factor correction equipment in the form of capacitor or other things. So maximum efficiency at say 0.8 or 0.9 power factor will be this one. Now the question is that where do I like to have this maximum efficiency, X? For example, as I told you, if you consider a 100 kVA transformer, and if you have the transformer is so designed that the value of X is 0.8, then what you see is this: the maximum efficiency will occur not at the full load condition 100 kVA, 80 kVA. The moment you want to operate the transformer at its rated kVA, its efficiency will go down definitely, because it will fall this way. Generally, suppose you are given a choice where what value of X you would like to have. Suppose a transformer, if it is 100 kVA, why I have purchased 100 kVA transformer? I must see that it is operated at its full rating. That's why 100 kVA transformer has been purchased. So what will be then your choice of the value of X? You would like to have 1. If X is 1 and transformer is operated to its full capacity round the clock, then you will get the highest efficiency possible. Are you getting? However, the story does not end here, because of the fact that you must suppose in your hostel or in your houses, power comes from a distribution transformer, is not at the lowest level. What is the voltage? 220 volt you get. Suppose let us assume this is the 220 volt transformer which is supplying say normal consumers in a residential locality. It is supplying power to that. Do you think the loading on the secondary of the transformer round the clock is fixed? No. You are now attending class. Your hostel load is 0. Therefore, it is not that the decision that the transformer should have X equal to 1 is to be deeply seen, considered. That is, really it is to be 1. In the peak hours, the loading will be perhaps rated. Are you getting? So, taking all these things into account, it is not always true that X equal to 1. Of course, if you know a transformer whose loading on the secondary side will practically remain at its rated condition round the clock, then go for X equal to 1. For example, of course, I have not differentiated between a distribution and power transformer. Just I will give you some very basic idea to distinguish between these two kinds. Say distribution transformer. Distribution transformer. And another transformer, another kind of transformer is called power transformer. Power transformer. Distribution transformers are the transformer at the lowest level, which generally supplies your residential capacity. Now, in our earlier lecture class, I gave you some idea of the generating station, then transformer, it is voltage up, then there will be supply given to big industries, and then ultimately it comes to small consumers like domestic consumers in this form. Now, suppose this is the generating station. The transformer here is called the power transformer. I will tell you why. Power transformer. And at various levels of voltage down, because it is EHT 400 kV say transmission, then there will be big industries who will purchase power at say 33 kV, 120 kV. They will purchase power. Maybe big industries, and after several level of transmission, I mean lowering the voltage, some distribution transformers will be locally this one. This picture you just keep in mind. What I am trying to tell is very simple. The idea is, now look at this transformer. This transformer which is handling the total power of the system. And look at this fellow, distribution transformer, perhaps supplying a IIT campus residential complex or other things. Now, when we say that the loading on this transformer changes round the clock over a wide range, perhaps it is now under no load, that transformer practically. But the power transformers, the percentage of this power handled by this is quite small, considering the industries at high voltage it has to supply, things like that. And as you know, industries will be working round the clock, say steel plants, big industries, 8-hour shift, 24 hours, this transformer is loaded. So if you look at the loading of this transformer, it is not really undergoing any no load condition or things like that. The sum total of all the loads will be handled by this transformer, and this transformer capacity, if it is suppose say 100 MVA transformer, the whether this fellow is there or not, this load is there or not, it will hardly matter to the secondary of this transformer, because it is supplying the bulk load is your industry load. So if you compare the operation of these two transformers, we immediately understand that while this transformer will undergo severe changes of load round the clock, this fellow will not. Maybe its load variation on the secondary will be between say 95 to 100%. I think I have been able to make that point. Therefore, for this transformer, we would like to have X closer to 1 compared to this transformer. Are you getting? So for distribution transformer, another kind of efficiency is defined that I will discuss afterwards. That is called all-day efficiency. But I think this point you have understood. So depending upon, as you are telling, the nature of transformer and knowing the load cycle on the secondary of it, we should choose the value of X. It need not be 1 all the time. That I want to tell you. So this is called efficiency of the transformer. Now another important thing I will start today, that is called regulation of the transformer. Or let me finish all-day efficiency, and this will perhaps make sense. So for distribution transformer, another efficiency is defined, which is called for distribution transformer.
So for the open circuit test, so we found that the copper losses were negligible. So that means at that time X will be tending to infinity. So and then
No. You just try to understand. The output power is the short circuited element. See, what is the output? You just don't make a mix up between the short circuit open circuit condition to a load. Suppose during short circuit test, you are applying after all very low voltage, but secondary, suppose you consider what is the power here? 0. The power whatever is drawn is consumed in the resistance within the transformer. Are you getting? What we are interested in efficiency calculation, what is the power here in Z2 divided by the input power in kilowatt. Anyway, you think about it. Further clarification if necessary I will give you. Achha, for distribution transformer, as we have seen, the load will go on changing with time. So it is not fair to judge a transformer from the efficiency, the normal efficiency we have just calculated. What they call it, then they say you calculate all-day efficiency. All-day efficiency. All-day efficiency. And it is usually denoted by all day. The idea, the most important thing in this case is this one, that suppose it is a distribution transformer. The loading on the secondary of this transformer will go on changing round the clock. Sometimes it will be under no load condition totally, as if somebody is sometimes closing this switch for some hours and making it off, and that too S, value of S, that X is changing round the clock. So what they calculate is, however, but you remember when the transformer is opened, the primary draws that no load power, core loss. So to judge the performance of such transformers, all day efficiency or energy efficiency is calculated, not power efficiency. This is alternatively known as energy efficiency. Energy efficiency. Now suppose you do like this. Suppose round the clock, suppose first T1 hours in a day, beginning from say 6 a.m., you note down what is the loading on the transformer. Suppose it is S1, and the average power factor of the load is suppose cosine theta 1 for T1 hours. Say, are you getting 0 to T1 hours? First T1 hours. Then in the next T2 hours, suppose the loading on the transformer is some S2 at power factor cosine theta 2. For say next T3 hours, there is virtually no load on the secondary, power factor meaningless. In this way, I can make a complete chart. Say S4 cosine theta 4 like this. Suppose in the nth for Tn hours, for T1 hours, T1 is not a single hour. So first 5 hours, the next 3 hours. So this is suppose Sn cosine theta n. And suppose let S be the kVA rating of the transformer, rated kVA. S kVA is the rated kVA of the transformer. Now first I write down what do I mean by energy efficiency. So eta all day, how shall I calculate? Eta all day is defined as the kilowatt hour output in 24 hours divided by kilowatt hour input in the 24 hours. Tell me, what is the kilowatt hour output? Say kilowatt hour output. Here, if you make a column in the first one, kilowatt hour output in the first T1 hour, it will be S1 cosine theta 1 into T1. Remember, S1 is in kVA. S1 is in kVA. Similarly, this will be S2 cosine theta 2 T2. Like this will be Sn cosine theta n Tn. Here, this T1, T2, T3, T4, Tn is such that T1 plus T2 plus say Tn, this is say 24 hours. This we'll see. In that way, we'll grade the loads or loading on the transformer. This is 24 hours. The sum of all the time intervals are 24 hours. Then the output is very simple. Here it will be S1 cosine theta 1 T1 plus S2 cosine theta 2 T2 plus this one. Last term will be the last hour Sn cosine theta n Tn. So this thing. So in below, what will be the total input energy? This numerator, that I am not repeating. This one, whatever is there, this thing on the top, plus the energy losses I have to calculate and calculate correctly. Tell me, what about the core loss energy? What should be the term? So it will be simply 24 into P core. Because one should not be under the impression when the transformer is under no load condition, I will also switch off the supply. That you are not supposed to do, because you do not know, somebody may just go to hostel now, want to switch on light. So supply authority has to keep his primary energized, no matter whether there is a load on the secondary or not. That I think is very clear. So this will be, this core loss is to be supplied 24 hours. So it will be 24 into P core, and all the things in kilowatt. Now tell me this one, say first T1 hours. Suppose PCU is the full load copper loss. What will be the first term? Suppose PCU is the full load copper loss. Right. It will be S1 by S whole squared into PCU into T1. This way it will go, S2 by S whole square, PCU T2, and so on. And lastly, Sn by S whole square, PCU into Tn, where express PCU P core in kilowatt, P core in kilowatt, PCU in kilowatt. So it is the energy efficiency which should be judged, or the value of which should be seen in order to purchasing, when you purchase a distribution transformer, rather than its ordinary efficiency. Because in case of distribution transformer, the primary remains energized for 24 hours. So that power loss 24 into P core, and particularly during no load operation, it just goes as waste. So this way one can distinguish between all day efficiency and this one. However, for a power transformer, where the secondary load substantially remains constant at its rated value or near rated value, the efficiency, ordinary efficiency you calculate and try to maximize it in this way. Now I will tell you about the regulation of a transformer. Regulation. What is meant by it? The concept of regulation is very simple. Suppose you have a battery, just a simple battery. How a simple battery will be modeled? Its EMF and its internal resistance, is not? And these are the two terminals of the battery. This is the equivalent circuit of a battery. And here you connect the load, say a lamp or whatever it is. Now obviously, when the switch is opened, that is battery is under no load condition, the voltage here will be E. It will register E if you measure with a voltmeter. However, when you load the battery, this voltage will be certainly less than E because of this IR drop in its internal resistance. Therefore, what we note here, that during no load condition, the voltage available across the terminal of the source is different from the voltage available when it is loaded, is not? So this change of voltage is measured by the term regulation from no load to full load condition. For example, after loading, if you find this voltage is V, you define regulation as this one. Per unit regulation, that is change in voltage from no load to the full load condition divided by this no load voltage, is what is known as regulation, and it is denoted by this curly R. And in percentage, of course, you multiply it by 100. Percentage regulation you will get. So what do you think? Regulation should be high or low for a source to be a good source? Low. It should be as low as possible. I mean, if R is 0, then it is. Because then, if regulation, this internal resistance is large, then as you can see, with degree of loading, the voltage applied across the load will change. Things like that will happen. Is not? We should see that the regulation of a source is as low as possible. Because all equipments are manufactured with a certain voltage to be applied across it. That should not vary too much. Okay. Similarly, our supply authority is committed to supply voltage, not at a fixed level 220 volt. They can play with it, but they are rather committed that 2 to 5% some regulation they will maintain, such that you are sure your voltage may go up, say 220 plus 5% of that, or 220 minus 5% of that. Are you getting? So this is the regulation. Now in a transformer, since transformer, from the secondary of the transformers, various loads are supplied, so the voltage changes from no load to full load condition can be similarly found out, and that is called regulation. So to obtain an expression for regulation, what we will do is this: we will refer to the approximate equivalent circuit. That is this one. Say refer to primary. I am drawing. This parallel branch is here. This is RE1, this is XE1, and here is your transferred load impedance, whatever is there, Z2 dashed, and this is your V2 dashed, and this is your V1, and this is your I2 dashed. Now, first, before refer to this equivalent circuit, just let me tell you how you measure regulation. Measurement is very simple. What you do, suppose a transformer is given, whose rating is known, say 5 kVA, 200 stroke 100 volt transformer, 5 kVA transformer. I want to find out its regulation. What I should do? I will energize this with 200 volt supply. And I will connect a load here on the secondary side. So first I will measure the voltage available here with this switch open. See, I am telling how will you measure the regulation. Let us not go into any mathematics. So transformer is given, I will give 200 volt and I will get some 100 volt here under no load condition. So that voltage I will record. Okay. So that voltage, then I will put load, and preferably the rated load, rated current, and at a specified power factor. So note down the voltmeter reading. Under no load condition. And also at rated load condition. So regulation will be how much then? Suppose this is the reading V0 and this is the V rated condition reading. Then your regulation, you will simply tell it is V naught minus V rated condition voltage divided by V naught. Now this same thing can be done experimentally, no problem. But what we will try to do that whether from the equivalent circuit we can quantify those things and get an expression for calculating regulation without performing actual test on the transformer. That is the objective of deriving a formula for calculating regulation. Now to this equivalent circuit, if you suppose this is the equivalent circuit, and here is the load. Suppose let us call with load connected, this voltage is V2 dashed, and this is RE1, XE1, and this is the voltage applied, V1. Now if you draw the phasor diagram, how it will look like? Suppose this is your V2 dash, take this on reference. This current is I2 dashed. Suppose it is a lagging power factor load, and this is the power factor angle theta 2. Then when this switch will be opened, what will be this voltage? It will be V1 only. Suppose you imagine this circuit is opened, so this voltage will be same as this voltage because no current is flowing. But anyway, now let me get V1 from this phasor diagram. This will be I2 dashed RE1 in phase with I2 dashed, and then I2 dashed XE1 will be this one, and your this voltage will be, I have drawn on a larger scale so that we can understand. This V1 you will be getting. Now remember, while defining regulation, it is only the magnitude of the voltage which is considered. Okay, that is the voltmeter readings only you consider. Phase angle you need not bother. So regulation of the transformer will be this way: this length minus this length divided by this length. Because of what? Because as a user of the electricity, I am interested the magnitude of the voltage. What phase shift it has suffered from the initial voltage, it does not matter to me. I must get 220 volt 50 hertz supply. Are you getting? So from the secondary of the transformer. So how magnitude of the voltage will change, that is important. So the regulation can be here in this case will be defined as only the magnitude V1 minus V2 dashed divided by V1. Because V1 will be the voltage when no load is connected. Today only I will do this one. So note that if you extend this one, or you can write it like this. This is suppose O, this is suppose A, this point, this is suppose B, this is suppose C. I can say that the regulation will be this length OA minus OB divided by OA, this length. So I will request you that you try to find out some expression by applying simple geometry, remembering the fact that this angle will be quite small in a good transformer, this one. So next day I will